supposed to be a lightning talk, beginner's lightning talk, so it's supposed to be short. And I kind of expect that you know this guy from many talks, very important talks. One of the most important talks was in 2013, the talk called C++ Seasoning. And the message of this talk essentially was no raw loops. So who of you is using algorithms? So a lot of algorithms. Okay, very good. A lot of people use algorithms, and this is a good thing. Yeah, you should definitely use a lot of algorithms. So, which means you can very quickly tell me the algorithm that is used in this L2 norm. So, I used the for loop. I shouldn't. I should use an algorithm. But which one? Louder? Accumulate is one option. There's something better. There is reduce. There's something better. Okay, there is inner product. So this is an inner product, perfect opportunity for inner product. Now the question is it actually worth to invest into inner product? So there is a very cool tool that you can use. I actually hope you already know it. Compile Explorer, which might give you exactly the idea if code is equal, whether you're writing a for loop is the same as using the algorithm. Side you see C++ code. This is exactly what I showed you before. On the right side you see the assembly code. So I don't want to go through all the details in this assembly code, but roughly, very rough comparison, we have 59 lines of assembly code on the right if I'm using the for loop. Now I uncomment the algorithm. Sorry, we cannot really see it. Okay. No, not too bad. It's a lightning talk. If you only get half of it, doesn't matter. So on the left, I have now used the inner product instead of the for loop. On the right, 59 lines of assembly code. As I said, a very rough comparison, but it kind of is an indication this is exactly the same piece of code. So of course, inner product is kind of better. Kind of. Well, I go back to my editor and I would like to do better than inner product. So first of all, let me just benchmark this little piece of code. So I compile, I use GCC 7.3, C++ 17.03 of course, and I remove all the debug symbols. Okay, let's see. It takes a little too long, but this is my machine. This is not because it's so complicated code. Yeah, I need a new one. It's 8 years old. I'm not to blame. But it's still working. I mean, look at the bright side. By MacBook for life. Not good for Apple, but it's actually, it's truly slow. It's okay. Whew. So, I run it, and what you see is mega flops. So I benchmark it in a reasonable fashion, of course. This is just the number 807 megaflops. So, yeah, 807 is the top value. All right, now just for comparison, let's use inner product, because of course inner product is the tight competitor. So I uncomment this as well. Probably it's running faster now because now everything has been loaded to cache. Else I have to tell another joke again. Okay, see? Now it's working. And, okay. Not exactly the same numbers, of course, but within the range of measurement accuracy, it's exactly the same. So this is exactly what I told you. Now I want to do better. Let's go back to my for loop. And I try to use a technique that is known from HPC. So high performance computing, I actually use two loop operations at the same time. This is called loop unrolling. What I want to do is I want to traverse the loop in bigger steps. So this is now unrolled by a factor of 2. It's not exactly correct anymore because now I'm missing the last element. It's strictly speaking only working for evenly sized vectors. But okay, this is not the most important piece of information now. So I save, I compile, and yes. What do we get? Okay. Not a real improvement. It's exactly the same, right? 807, this is what it was before. So no gain. So to some extent, perhaps Chandler Carruth was right in his Meeting C++ 2015 talk. Loop unrolling doesn't pay off, and the compiler is doing it well enough. Well, I do something else. Instead of having one norm, let's have two of them. So I probably initialize them, 1, 2, and of course I use the sum of these two at the end. Yeah, so it's hopefully exactly the same piece of code. All right. I compile it again, and I run it. That's amazing, isn't it? Factor 2 performance. And this is not something that happens by accident. I run it again, and it's exactly the same again. I hope this is a little impressive. Yes, a slight code change, and suddenly you have factor 2. Why? Well, you have 2 arithmetic units in your CPU. Unfortunately, you're only using 1 if you just run the for loop as before. So going back real quick. In this little piece of code, you actually only use 1 of these arithmetic units. Because you have a data dependency, you always sum up to this one norm. And of course, I have to wait for this operation to finish before I can do the next one. If, however, really unroll properly, then suddenly there's an opportunity. I can use 2 arithmetic units. I can do adds and 2 floats at the same time. And so suddenly the performance is really twice as fast. That is pretty cool. So no questions in between. It's a lightning talk. So, no raw loops. Is this really something that we should follow? Well, what I did tell you is compilers do not unroll particularly well. This is an experience I did, and this is why I was arguing with Chandler. Chandler didn't believe me. Actually, 3 years later, it's still the same. So loop unrolling can improve the performance, quite easily so. So especially in these algorithms where you have the opportunity to use 2 arithmetic units instead of just 1. But, well, the advice is still true. No raw loops. You should not use raw loops now instead of these algorithms. What you should do is just to create other algorithms. So call it unrolled accumulate, unrolled reduce, unrolled inner product. Create new algorithms, use them in your product or code, whatever. That is the right thing to do. Still, the advice is actually correct. We still have to just update the implementation of these algorithms. And now you're asking which ones are affected? Well, mostly the numerical ones. So accumulate, inner product, reduce, and of course transform, reduce, and the partial sum. That is the ones that you have to take a closer look at if you're using them in your product. Okay, now it's time for one question. Yeah.
What was the type of your vector elements?
This was doubles, I believe.
Does it change if you compile with fastmath?
Let me check first. Double. It was double. And does it change if I use fastmath? So let me just check. Probably no. I would also say no, but I like this.
I don't know what they call them on GCC. Fastmath, I don't know it by heart.
I don't know. So.
Because my suspicion would be that he's actually not allowed to do this transformation that you.
Correct. That is actually something that has to do with semantics. It's not easy to do it. You have to know a little more. However, in this particular case, that's kind of something that always works. Yeah?
But easy to be fast, difficult to be correct.
Okay. So.
Yes, because the floating point associated.
So it's floating point associated. You will never get the same result. So if you use accumulate, it's the same result because it always does the addition or all the stuff from the first element to the last element. With reduce, however, you cannot count any particular result. It's floating point.
Half back, then you can use simple operation.
Exactly.
You have,
exactly. It's different result. Yeah.
No, but then you could use it's like multiple contributions, right?
All right. So probably this is now a very good point to have a long debate, but it's supposed to be a lightning talk. So let's switch.
Thanks.